Right, as I mentioned, this is a last tutorial of Math 102, and I plan to do what I did in summer, which is at the end of the tutorial, I want you guys to turn on your camera and we can take a group picture together. It's totally optional, so no pressure. If you have a look at the tutorial worksheet, this week we have 6 pages, which is impossible for me to finish. So we will pick some questions to do. The rest of them, I want you to try to finish them. I will either post a solution or I will post a video or I can do another review session. It's really up to you. So vote in the chat. What do you want me to do for the questions that we don't have time to finish? Let you guys vote while I talk about our topic. So this tutorial I plan to do divisibility and relation. I used some of Daria's tutorial activity and I added some other questions in there because I feel like it's important as well. So we'll try to finish as many questions as possible. For the rest of them, we'll do whatever you vote. You decided to do. So I will decide at the end of the tutorial once everyone will share your opinion. So first of all, let's talk about the division algorithm. This should be really simple for everyone because this is basically high school material. So if you have a number A, you can write A as Q times B, A as Q times B plus R. Okay, notice that your R has to be strictly smaller than B. That's really important. Just gonna underline it as well. So notice that your R has to be smaller than B. This is really important. The rest is just, I think you guys know already. GCD, the greatest common divisor is the largest integer. Okay, make sure it's integer. The largest integer that divides both numbers. So if GCD AB equals to 1, then we see A and B are relatively prime. I'm sure you guys know this already as well, so I don't want to talk too much about this. But there is one question I want to ask. What if we have GCD, let's say 8 and 0? What is a GCD of 8 and 0? Well, we know that A, B cannot be both 0, but what if one of them is 0? Read this part, the largest integer that divides both numbers. Not 1, not 0, 8 is a correct number. Okay, 8. Why is that? Because any number is divisible by 0. Okay, so in this case it will be 8. Yes, except itself. So that's why we cannot have GCD of 0, 0, but we can have GCD of another number and 0 because any number divides 0 except itself. Does that make sense? Okay, that's a common mistake. That's why I wanted to mention. But other than that, it should be okay. Proposition 6.2.2 is just saying that GCD of AB equals to GCD of A minus KB and B. This is pretty useful, except, especially when they just ask you to find the GCD of two numbers. If it's like, if they didn't say you have to use the algorithms, you can just use this proposition, which is it's basically the algorithm, but sometimes it's easier to write. Anyway, let's look at the first example. Find the GCD of the following. I'll give you some time to work on this while I get some water. But yeah, try this question. If you want, you can write. Let me see if I can let you write. If you want to share your answer, I think you could annotate on share screen. Yeah. So if you want to share your answer, go ahead and annotate on the screen, and we'll take it up later. Sit. Brownie, come back. Anyone else want to try another question? So one of you is trying number 2. Anyone want to try 1, 3, or 4? Well, 1 is the easiest one. So try that. Someone? Oh, someone's writing it already. Okay, cool. Nice. What about 3 and 4? Anyone's trying those? No one's trying number 3? Okay, if you don't know how to do number 3, try 4. At least try 4. 4 is not a hard one, right? For 2, it's 12 to the power of 3. Yes. It's okay. Anyone want to try 3 and 4? Or do you want me to take it up? No one? give you slightly more time. Not confident about 3 and 4. Okay, it's okay. Okay, so let's look at 1 and 2 first. So for number 1, GCD of n plus 12 n plus 13 equals to GCD of n plus 12 and n plus 13 minus n plus 12. Exactly, so you use the proposition we just talked about, which equals to GCD of n plus 12 and 1, which equals to 1. Okay, that's correct. We annotate this is correct. So this is correct. Number 2, so 12 to the power of 3 equals to 4 times 3 to the power of 3, which equals to 4 to the 3 times 3 to the 3. And then 15 to the power of 4 equals to 5 times 3 to the power of 4, which equals to 5 to the 4 times 3 to the 4. So the GCD is 3 to the power of 3. Is that your answer? Yep, it's correct. This is correct. But why is it 3 to the power of 3? Do you mind explaining? It's correct, but I want you to tell me why is that? Prime factors, yes. Okay, cool. So 3 to the power of 3 is the largest common divisors of those, okay, because the other ones are. One thing I wanna say is it would be better if you write 4 to the power of 3 here. So it will be better if you write, it will be better if you write 4 to the power of 3 as 2 to the power of 6, because 4 is not a prime. Okay? Everything else is good. Alright, so number 3. So for number 3, we have 32 and then 44 plus 32 to the power of 6. Well, what you can do is you can use the proposition we mentioned before. So this is the same as 32, 44 plus 32 to the power of 6 minus 32 to the power of 6. Or let me write it in another way, which makes more sense to you. Minus 32 times an integer. Okay, so in this case, let me just use another color. So in this case, this is your A, this is your B, and this is your A, and this is your K. So A, B equals to A, B minus AK. Does that make sense? It's by the proposition we just mentioned before. Okay? So this will give you 32, 44. And what's a GCD of 32 and 44? Anyone know? Okay, let's continue then. Which equals to 32. 44 minus 32 is what? It's 12, which equals to, so let's do it again, 32 minus 12. No, 32 minus multiples of 12. That's gonna give us 8 and 12, which equals to 8 and 4, which equals to 4 and 0, which equals to 4. Okay? Any question? Question? Can we stop at 8, 4? Well, if you can use 8, 4 to get the GCD equals to 4, then sure. Any other question? Not from you. Okay, cool. Number 4, someone said it's 15. It's correct. Since I used the proposition to do this question, I'm gonna use algorithm to do the second question, because in the later question it's gonna be helpful to use the algorithm. So let's try this. So we have 6, 15, and 8, 10. I'm gonna start with a bigger number, which is 8, 10. 8, 10 equals to 1 times 6, 15 plus 195. Okay, and then you put this number here and put this number here. So you'll get 6, 15 equals to a number times 195 plus another number. So that's gonna be 3 times 195 plus 30. So what I did is I put this number here, put this number here, and I do the same thing. Next line, I'll have 195 equals to something times 30 plus another number. That's gonna be 6 times 30 plus 15. And then 30 equals to 2 times 15 plus 0. So we reached 0 already. So this number is gonna be our GCD. Therefore, GCD of negative 6, 15 and 8, 10 equals to 15. So this number is what we're looking for. Any question? Well, you can use the other method, which is using the proposition as well. Okay, so you can do this as well. If they didn't ask you to use the algorithm, then you can use this as well. Any question? Yes, exactly. Question? If no question, I'm gonna move on to the next one. Okay, so next example. Oh, before that, let's talk about Benzo's identity. This is just saying that if we have two integers, not both 0, then there are mn, which are integer, such that a times n plus b times n equals to GCD of mn. Okay? It's simple but useful. Probably not as useful as in 102, but in upper year math courses, it's really useful. In 102, it's useful to solve this question. Find xy in integer such that 15 equals to 615x plus 810y. Well, if you realize that this example and this example, they're actually related, okay? GCD is 15, we have 615 and 810. By Benzo's identity, we know that there must be two integer AB such that AM plus BN equals to the GCD of MN. So AM plus BN equals to GCD of MN. But how do we find those two integers? Give you a hint, you need to use this. You need to use this. So I'll put it here. I'll leave it here. And I'll tell you to find x and y, you need to use this. Another hint is that it's basically backwards of Euclidean algorithm. Bernie, give it to me. Give it to me now. Bernie. So A is x, y is m, n, or a, b. Okay, so look at this. 15 is a GCD of mn. Which equals to a times m, so m equals to 16. X is your a here, and n is a 10. Y is your b here. Okay, does that make sense? So by the identity, we know that there exists such x and y. Now I need you to find such x and y. Brownie, do you guys want to see my cat? Let me see if I can find my cat. I'll show you. Come on, I want to see you. Brownie, go away. Go away, Brownie. Okay, there we go. Do you guys see him? He doesn't get along with my dog. They fight every single day. No. Say hi to everyone. Say hi. Yeah, he wants to leave. Okay, let me put it back. And I'll show you my dog too. Right? Just give me a moment. Let me show you my dog. I need to get rid of the visual background. Bunny, Bunny, come. There we go. Bunny, sit. Sit. Hello? Wow, it just ignored me. Anyway, that's my dog. Wow. My dog's not listening to me. Anyway, let's get back to this question. So, what you need to do is you need to work backwards using this. What we want to do is we want to start with 15. So I'm going to rearrange this equation. So we will have 15 equals to 195 minus 6 times 30. Okay, so that's my first one. Now, I can write 30 as this. Excuse me. So we can rearrange this equation and write 30 as... Brownie, shut up! Brownie! See, they don't get along with each other. They fight. Now they're fighting. Anyway, this equals to 195 minus 6 times. So we rearrange this equation. 6 times 615 minus 3 times 195. Okay, let me give them a number. So this is 1, 2, 3. So this is by 1, by 2. Now what I'm gonna do is notice that I have 195 here. I have 195 here as well. So I'm gonna open a bracket and collect those two like terms. So that's gonna give me 195 minus 6 times 615 plus 18 times 195. Okay, now I can collect them. So that's gonna give me 19 times 195 minus 6 times 615. Well, if you look at equation 3 here, we can rearrange this equation and we can write 195 as 810 minus 615. So this equals to 19 times 810 minus 615 minus 6 times 615. So this is by 3. And this will give you 19 times 810 minus 19 times 615 minus 6 times, well, I wrote 65 with 615. And you collect those two like terms. Okay, you'll get 19 times 810 minus 25 times 615. Now we reach the final equation here. That means our x is negative 25 and our y is 19. Any question? Question? Anyone? Question? Does this make sense? So basically, you're just working backwards using Euclidean algorithm. Okay? Even if it doesn't make sense to you for now, you can try it at home and convince yourself. I think it's pretty clear. Okay? If you have any question, email me. Is it possible to do this without doing the original algorithm? I think this is a pretty typical way of doing this. I haven't seen any other way of doing this, to be honest. Any other question? Line 2. Here? Okay, so basically, I got this because if you look at equation 2 here, I can rearrange equation 2. So I know 30 equals to 615 minus 3 times 195. So I substitute this here because I have 30 here. Does that make sense to you? Okay, and I did the same thing here as well. Okay, so basically I'm just rearranging my Euclidean algorithm to do this. Yeah, exactly. Any other question? Okay, cool. So Euclid's lemma, it's saying that if we have a prime number and a and b are integers, if p divides the product of ab, then p divides a or p divides b. And I want you to use this to try example 3. I actually did a really similar question before in one of my office hours. So if you were there, you should be able to recognize that I proved square root of 2 as an irrational number. It's really similar to this. So try this. No, Brownie, no. Sit. Brownie. No, too loud. You're being too loud, baby. Yeah. Sit. Good boy. Head. Good boy. Other hip. Good boy. Good boy. Look at me. Good boy. By the way, my dog just lost 3 teeth. I think he's changing teeth. Do you guys want to see his teeth? I don't know if you guys can see it. This is one of it. Can you guys see? No, he didn't hurt himself. It's like it's growing, you know. So you know, like when children, yeah, baby tooth, exactly. When children they grow up, like during teenager, they change teeth. This is our second one. Oh, can you even see it? Yeah, here. And there is a third one. Got blood everywhere on my bed. pretty cool. I collect all of them. Ready? Oh, I think you guys said do review session. When do you guys want me to do it? Today? Tonight? Or tomorrow? I can... Tomorrow... If we do tomorrow, we can only do tomorrow night. Because I'm teaching tomorrow afternoon. Like 3 to 3. Yes, you prove by contradiction. Exactly. Like around 3 to 4:30 I have to teach. 1 to 3 I have work as well. Tonight. Yeah, we can do tonight. We can do tonight. Tonight should work for me. Oh yes, it should be a natural number. You're right. Oh, natural number. I think I might have a cold. Cause did you guys go out recently? It's snowing today. And I think it started to snow since last night. It's like all white outside. I'm dropping so many things. Oh, that's cool. Gonna start showing snow. I'm so glad I moved to downtown and I don't need to do it anymore. Before, I lived in Mississauga and I have to do it every winter. It's really annoying. Cause like in my place, it's just me and my sister, so we don't have anyone else to do it for us. It has to be either me or my sister. And my sister is too young to do it, so I had to do it, and it's really annoying. Now I'm just glad I moved to downtown. Alright, let me start writing my proof because we're running out of time. Well, for the rest, we'll do the rest tonight. We don't finish this, we'll do the rest tonight. So, for contradiction, assume that square root of 2n is a rational number since what time tonight? We can do 7, after 7, is that good? After 7 o'clock. Yeah? Okay, cool. Then after 7. So after 7 p.m. and onwards. Oh, okay. So as soon as it's a rational number, then we can write this as we can write square root of 2n equals to a over b, where my a, b are integers, b is not 0, and GCD 3 hour 8 minutes from now. For what? For the and GCD AB equals to 0, yeah. Equals to 1. Yes. Then we can write this as 2n equals to a over b squared, which means we have 2n b squared equals to a squared. Okay? So when we reach here, this means that 2 divides a squared. Any questions so far? Is it okay if I write 2n as 4k plus 2? Sure. Yeah, you wanna express n as a odd number. Yeah, sure. Just make sure you define your k, okay? So if you wanna write it like that, then you have to say for some k natural number. But if you wanna do that, sure, no problem. Anyway, this means that 2 divides a square, and by the Euclid's lemma, we know that if P2 is a prime number, if P divides AB, in this case A and B are the same, they are both A, then P divides A or P divides B. So this will give us 2 divides A. By the lemma, okay? Since we know 2 divides A, we can write A as 2K, where K is an integer, and we can substitute this back to this equation. So this will give us 2 b squared equals to 2k squared, which will give us 2 b squared equals to 4k squared, which is the same as b squared equals to 2k squared. Okay? Since we have this, we know that 2 must divide b squared as well. So wait, we have an n here. Yeah, it has to divide b squared as well, since n is odd. Okay? If we don't know n is odd, then we cannot make this conclusion. Since we know n is odd, which means it's not divisible by 2, so we know that b squared must be the one that is divisible by 2. Okay? Alright, so by the lemma, this means 2 divides b as well. Now we have 2 divides a and 2 divides b, which means the GCD of AB is at least 2. Actually, not this, which means it's not 1. Brownie, no. So this is a contradiction because we assume that GCD of AB equals to 1. Any question? Question? Anyone? If not, then our last activity is let's turn on the camera and take a group picture. So, ready, guys? Oh, there we go. There we go. We have some people. Okay, let me change this view to gallery view. All right, there we go. Anyone else want to turn on your camera? There we go. We have one more. Let's wait until 4 o'clock. So 2 more minutes and see if anyone else want to turn on their camera. Anyone? Nice to see you all. It's the first time I see what my students look like. You guys can unmute yourself and talk. I mean, it's the end. It's the last tutorial. Okay, I suppose the other people don't want to turn their camera on. So let's do this. 3, 2, 1. Okay, let's take another one. 3, 2, 1. Okay, there we go. Okay, bye guys. Nice to see you all. Good luck on your exam. I'll see some of you at 7 p.m. today, I guess. Bye.